Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. As you already know that we are going through structural biology techniques and currently we are in the module of spectroscopy. Today we have already discussed about the basic of spectroscopy, CD, UV, fluorescence. Today we are going to talk about another technique which are very important in protein. People have not used it a lot, but it is used to get fingerprints, and I am talking about IR spectroscopy. Also I would discuss about another one which is Raman, because you always know IR and Raman comes together, and I will talk in the later class how Raman have a very important role in determining protein structure. So, let us start with infrared spectroscopy. As you know, the electromagnetic spectrum and infrared is in between UV and microwave. Infrared is generally influenced by vibration. When I say vibration, I mean bending and stretching. So, let us think about, you have molecule or atom A and B connected through a bond. As we have discussed, we now know that this binding could be explained in terms of connectivity as a spring. So, now it would show stretching. Is this stretching is characteristic? If it is characteristic to anything, then it would help us to characterize a particular molecule, solvent, functional group. Again, if you have 3 atoms, again you connect them with spring and you look at the bending. So, that is where infrared or IR spectroscopy works. So, IR spectroscopy is concerned with the study of absorption of infrared radiation which causes vibrational transition in the molecule. IR spectroscopy, also known as vibrational spectroscopy, because it deals with the vibrational transitions which we have discussed here. IR spectra mainly used in structure elucidation to determine the functional groups. As I told you, are getting a particular bending or stretching. If it is characteristic to some molecule, then you get the identification there. So, you get a particular spectra of that functional group. Now, you see the position of the infrared. The infrared is 0.8 micrometer to 1000 micrometer wavelength. It could be divided into 3 distinct parts. One is near infrared, which is 0.8 to 2 micrometer, middle infrared, which is 2 to 15 micrometer, and far infrared, which is 15 to 1000 micrometer. Most of the analytical applications are confined in the middle ear region because absorption of functional groups relevant to study biology and chemistry are primarily present in this region. As I told, the covalent bond can vibrate in several modes including stretching, rocking, scissoring. If you see symmetric stretching, antisymmetric or asymmetric stretching and bending or scissoring. So, the most useful bands in an infrared spectrum correspond to the stretching frequencies, and those will be the ones we will focus on. Which are the ones? These are the ones: symmetric and asymmetric stretching. Transmission versus absorption. This is everywhere we go in spectroscopy, we look at them. When a chemical sample is exposed to the action of infrared light, it can absorb some frequency and transmit the rest. Some of the light can also be reflected back to the source. We have talked about interaction of matter with any light source, and absorption, scattering, transmission, reflection, all are possibility. So, if you look at, you have a IR source, it go to the chemical sample or the sample which you put under experimental condition, then the transmitted light goes to the detector and detection happen. The detector detects the transmitted frequencies, and by doing so also reveals the values of the absorbed frequencies. The absorption spectrum, the IR spectrum which we see is basically a plot of transmitted or absorbed frequencies versus intensity of the transmission or absorption. So, if you see here absorption and frequency, absorption is percentage, frequency is in wave numbers, centimeter inverse. Frequencies appear in x axis in unit of inverse centimeters, wave numbers, and the intensities are plotted on the y axis in percentage units. This is transmission, this is overlapped, sorry. So, this is transmission. The graph shown here is the spectrum in transmission mode. So, two modes you will see: absorption spectrum, absorption mode, transmission spectrum in transmission mode. This is the most commonly used representation and one found in the literature. So, while we will go through the literature, you will see this type of spectrum are common. We will use this in our representation also. IR spectroscopy band, IR bands can be classified as strong. If you see such a long band, you will see strong, medium like this, and weak like this, depending on their relative intensities in the infrared spectrum. IR active bonds. Not all covalent bonds display bands in the IR spectrum. Only polar bonds do so. These are referred to as IR active. The intensity of the bands depends on the magnitude of the dipole moment associated with the bond in question. Strongly polar bonds such as carbonyl groups produce strong bands. Bonds with medium polarity and bonds with asymmetric nature produce medium bands. Weakly polar and symmetric bonds produce weak or non-observable bands. So, strong band, medium band, weak band, no band. These are the categorization that would happen depending on the dipole moment associated with the bond. Signal strength to the molecule, if you look at carbonyl group, aldehyde and ketone, these are strong. If you look at C triple bond N, they are medium. If you look at C triple bond C, they are weak. And if you look at C triple bond C with methyl group in both the sides, so giving the, so this is asymmetric, this is symmetric. So, there is not observable or no band in IR spectroscopy, not any one we will talk about. IR spectroscopy band shapes. Infrared band shapes come in various forms. Two of the most common are narrow and broad. Narrow bands are thin and pointed like a dagger, we will see them later. Broad bands are wide and smoother. A typical example of broad band is displayed by hydroxyl bonds such as those found in alcohol and carboxylic acid. We will see there, see here it is the hydroxyl group. IR spectroscopy for different molecules. A typical IR spectrum range for covalent bond is 600 to 4000 centimeter inverse. If you see here it is 600 to 4000, that is the range. The graph shows the region of the spectrum where the following type of bonds normally absorb. If you see NH, OH, CH, they absorb within 3500 to 3000, 2500 to 2000 it is C triple bond C and C triple bond N. Double bonds are within 1800 to 1600 and single bonds are actually characteristic, that is why it is they are characteristic. Characteristic means they do not change much. So, that is why if you get around this, you know these are these bonds. Like a Serb band around 2200 to 2400 centimeter inverse would indicate the possible presence of a CN or CC triple bond. So, coming to different one, now you could see these are thin ones, we will talk about broad ones which we have shown already, that would be like hydroxyl we have seen. Nitriles display strong band around 2 to 50 centimeter inverse due to the presence of CN triple bond. So, here it is around 2 to 49 centimeter inverse. This band has a sharp pointed shape similar to the alkyne C triple bond C actually, but the C N triple bond being more polar, this band is stronger than the alkynes. Alcohol, the most prominent band in alcohol is due to the presence of OH or hydroxyl group. The band appears being strong and broad, covering a range of about, here if you see it's started around 3000 centimeter inverse and it goes around 3700 centimeter inverse. The sheer size and broad shape of the band dominate the IR spectrum and it is difficult to ignore. So, what it means, if you have a hydroxyl group, you will get a band, that is a surety. So, carbonyl compounds, the carbonyl compounds are those that contain the C double bond O functional groups. Among them we know that there are, this is the carbonyl group. Now, you have CHO aldehyde and ketone COR. In aldehyde, this group is at the end of carbon chain, because after that it is hydrogen. In contrast to this, in ketone it is in the middle of the chain, because so it is middle. The difference is the carbon in the C double bond O bond of aldehyde is also bonded to another carbon and a hydrogen, but considering the same carbon in a ketone is bonded to two other carbons. So, if you think here CH3 CHO, one carbon one hydrogen, CH3 CO CH3 two carbon. So, aldehydes and ketones show a strong prominent stack shaped band around 1710 to 1720 centimeter inverse, which is here. You will see here you get a band 17102 to 1720. This band is due to the highly polar C double bond O bond. Because of its position, shape and size, it is hard to miss again. Because aldehydes also contain a CH bond to the sp2 carbon of the carbonyl bond, they also show a pair of medium strength bands positioned about 2700 and 2800. So, when you are considering the this one, this is 1720 mostly picked and 1718 for ketone, and due to the aldehyde also have CH bond on the sp connected. So, they have a, if you see here 2720 and 2820, 2700 to 2800. If you look at carbonyl of ketone, this hydrogen is missing. So, this band you do not get here. So, that is one of the significant difference you could differentiate between a aldehyde and ketone based on IR spectrum. Coming to carboxylic acid. So, this is carboxylic acid containing compounds. So, if you see carboxylic acid, you get a carbonyl, you get a hydroxide. So, you get this OH and you also get the CO. These are the main ones, but you also get a CH stretch here. A carboxylic acid functional group combines the features of alcohols and ketones because it has both the hydroxyl bond and the carbonyl bond. Therefore, carboxylic acid show a very strong and broad band covering a wide range between 2800 to 3500 centimeter inverse. Here, if you see around 2800 to 3500. At the same time, they also show the stack shaped band in the middle of the spectrum around 1710 centimeter inverse corresponding to the CO stretch. So, this is 1711, which is 1720 for aldehyde and 1718 for ketone. Coming to amine group containing compounds. So, if you see amine, now get NH stretch. So, you get them the NH stretch in this region. You also get saturated CH stretch because it comes with other carbons. So, you get CH stretch here. The most characteristic band in amines is due to the NH bond stretch, and it appears as a weak to medium somewhat broad band, but not as broad as the hydroxyl group. So, this is weak, the polarity or the dipole moment is not so high. This band is positioned at the left end of the spectrum in the range of about 3200 to 3600 centimeter inverse. Primary amines have two NH bonds, therefore, they typically show two spikes that make this band resemble a molar tooth. So, this is what they got, the spike. Secondary amines have only one NH bond. So, you could differentiate between primary amine and secondary amine because you get the 2 and 1 and tertiary no. So, primary amines have two NH bonds, therefore, they typically show two spikes that make this bond resemble a molar tooth. Secondary amines have only one NH bond, which makes them show only one spike resembling a canine tooth. Finally, tertiary amines have no NH bond and therefore, this band is absent from the IR spectrum altogether. Coming to amides. So, amide, the amide functional group combines the feature of amines and ketones, because they have the keto group and amine group. So, the amide functional group combines the feature of amines and ketones, because it has both the NH bond and the CO bond. Therefore, amides show a very strong, somewhat broad band at the left end of the spectrum in the range between 31000 to 3500 for the NH stretch coming from here. At the same time, they also show the stack shaped band in the middle of the spectrum around 1710 centimeter inverse for the CO stage. If you remember, so they are showing it around here in this compound, they are showing around 1630 to 1660. So, we have seen in other compounds aldehyde 1720, ketone 1718. So, this is also a characteristic one. As with amines, primary amide show 2 spikes, whereas secondary amide show only 1 spike. So, we have look at this NH stretch and we get 2 pikes, because this is a primary amine. For secondary amine, we will get only 1. Again, one thing to add here, that amide band have other importance. As you know, the peptides in protein, which is our goal, have this amide group, right. We will see later there are amide 1 and amide 2 characteristic band, which help experimentalists detect the secondary structure of the protein using IR spectroscopy. So, as discussed here, and we have looked at different compounds, infrared spectroscopy is useful in providing information about the presence or absence of a specific functional groups. IR can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. IR does not provide detailed information or proof of molecular formula or structure like NMR or other techniques. It provides information on molecular fragments, especially functional group. As we have seen, the hydroxyl group, the amide group, the carbonyl group all have particular stretches, particular peaks, and that would help us to identify those functional groups presence in a experimental sample. Application: infrared spectrum is applied for compositional analysis of organic, inorganic and polymers, because as we have discussed continuously, they are excellent in identifying the functional groups. First application in biological and biomedical fields, for example, detection of water in biological membrane, for biological sample also where we do not know about the solvent and all, we will look at that later. Analysis of aircraft exhausts, measurement of toxic gas in fuels, combustion, gas analysis, all could be done with very good precision using infrared spectrum. So, application: determination of fingerprints. So, if you see for alkanes, they have stretches 2850 to 2970 strong, 1340 to 1470 strong. For alkenes, the double bond, again they have spectrum. So, for CH stretch, for OH stretch, for NH stage, C double bond C, C double triple bond C, C single bond N, C triple bond N, C single bond O, C double bond O, NO2. For all of them, they have fingerprints, they have a range of frequency, and if in the sample this functional group are present, we take the sample, do the experiment, get the peaks and match it with them. Detection of unknown sample, this is a very good technique for detecting unknown samples. Like if you see, we have a spectra of an unknown sample and we have the library of known standard compounds. Now, you match them, if it match, you know that what type of sample it is. Like if you see here, there is an unknown sample, we plot this sample against absorbance in the y axis and wave number in the x axis, and we get the spectra. The spectra exactly match with benzene. So, we know that this unknown sample is benzene. It is very easy, very convenient in detection of unknown sample. Determination of air contamination. So, if you see the data, we have carbon monoxide, methyl ethyl ketone, methanol, ethylene oxide, chloroform, and you get the concentration in ppm, you found the presence, and from there you could have calculate the how much air contamination happened. Solvent, again these are characteristic spectra of orthoxylene, metaxylene, paraxylene, ethyl benzene, cyclohexane. So, all of them are solvent. You have standard library of these solvents. So, when a new sample come and you do not know the solvent, you match the spectra and you determine the solvent. So, you have standard spectra for common solvents, you develop a library, and then what you need is to match with the unknown one. You get the spectra of the unknown one and match in the library. Fourier transform infrared spectroscopy, FTIR. FTIR is a technique used to obtain an infrared spectrum of absorption or emission of a experimental sample. An FTIR spectrometer simultaneously collect high resolution spectral data over a wide spectral range. This confers a significant advantage over a dispersive spectrometer, which measures intensity over a narrow range of wavelengths at times. So, more broader or wide spectral range you get, more generalized detection or generalized application the instrument could do. As we know, the term Fourier transform infrared spectroscopy originates from the fact that Fourier transform is required to convert the raw data into the actual spectrum. So, we are now going to the automation. So, the analog data is now converted to the digital data, and that makes the data processing quicker, the analysis more fast, convenient, accurate, and that is why a Fourier transform infrared spectroscopy is used. FTIR spectroscopy provide information about the structure content of the protein, but when I say structure content of the protein, unlike X-ray crystallography which we discussed, NMR spectroscopy which we discussed, which provide information about the tertiary structure of the protein, FTIR provides only secondary structure. If you remember our NMR module, I have explained how NMR makes its journey in determining the secondary structure of the protein and then go to the determination of the tertiary structure of the protein. Whereas, if you consider the technique of X-ray, you will clearly see that X-ray directly go to the determination of the 3D structure of the protein. So, NMR determine 2D structure, Fourier transform infrared spectroscopy also determine 2D structure. So, how it works? FTIR spectroscopy works by shining infrared radiation on a sample and seeing which wavelength of radiation in the infrared region of the spectrum are absorbed by the sample. As we have discussed as a general in the IR, each compound has a characteristic set of absorption bands in its infrared spectrum. Characteristic bands found in the infrared spectra of protein and polypeptide, which include amide 1 and amide 2 band. And now the amide 1 and amide 2 band, this arise from the amide bond that link the amino acid. If you see here, amide 1 vibration and amide 2 vibration, these are the cause of development of amide 1 and amide 2 IR band. The absorption associated with the amide 1 band leads to stretching vibration of the carbonyl bond of the amide. Absorption associated with the amide 2 band leads primarily to bending vibration of the NH bond. So, because both the carbonyl and the NH bonds are involved in the hydrogen bonding that takes place between the different elements of secondary structure, the location of both the amide 1 and amide 2 bands are sensitive to the secondary structure content of the protein. What this is talking about? So, as I told, this is the amide 1 and this is the amide 2. Depending on the how the hydrogen bonds are developed, depending on that there would be change in the stretching and bending, that would tell you the position or the sensitivity of the characteristic part of the protein and how this could be related to the secondary structure. Studies with proteins of known structure have been used. So, already there are study of the known protein structure and they help to develop the fingerprints here. So, actually some are fingerprints, which we say fingerprint, they are characteristic. Some are not characteristic, they are altering, but you take a lot of known samples, you collect, you record the data, you have your own library, and now matching with the library you can comment on the unknown protein. That is what happening here. So, I will now shift to scattering. You know, I talked about the interaction of matter with light, it lead to many phenomena like reflection, transmission, absorption, scattering, and as we have discussed earlier, the basic foundation of spectroscopy is the interaction between the light and the matter. So, now we will talk about scattering. Scattering could be defined as a change in the direction of motion of a particle because of the collision with another particle. If you see, the sunlight comes and hit the atmospheric particle and then it scatter. What is the effect of light scattering in making on nature? So, light scattering is responsible for various spectacular phenomena in nature. The blue color of the sky, if you see the bright blue sky, the color of water in the deep sea, you see the beautiful color, the reddening of the sun at the time of sunrise, you see, and the fading color of sunset, all of them actually can be explained on the basis of scattering of light caused by the earth's atmosphere. So, dear nature photographer, next time when you are publishing a nice photograph, please do not forget to acknowledge the effect of scattering on making your photo more beautiful. So, light scattering is a form of scattering in which light in the form of propagating energy is scattered. Light scattering can be thought of as the deflection of a ray from a straight path, for example, by irregularities in the propagation medium, particles, or in the interface between two media, the phase change. The deviation from the law of reflection due to irregularities on a surface are also usually considered to be the form of scattering. When these irregularities are considered to be random and dense enough that their individual effects average out, this kind of scattered reflection is commonly referred to as diffuse reflection, not scattering here. Most objects that one sees are visible due to light scattering from their surfaces. Indeed, this is our primary mechanism of physical observation. Scattering of light depends on the wavelength or frequency of the light being scattered. There are different type of scattering, like Rayleigh scattering, which is named after the 19th century British physicist Lord Rayleigh. It is the predominantly elastic scattering of light or other electromagnetic radiation other than light by particle much smaller than the wavelength of radiation. Mie scattering occurs when the diameter of atmospheric particulates are similar to or larger than the wavelength of the scattered light. Dust, pollen, smoke and microscopic water droplets that form clouds are common cause of Mie scattering. Tyndall scattering of a beam of light by a medium containing small suspended particles, for example, smoke, dust in a room, which makes visible a light beam entering a window. The effect is named for the 19th century British physicist John Tyndall, who first studied it extensively. Brillouin scattering, this is an effect caused by the non-linearity of the medium, specifically by that part of the non-linearity which is related to acoustic phonons. An incident photons can be converted into a scattered photon of slightly lower energy, usually propagating in the backward direction and a phonon. Raman scattering, this is the inelastic scattering of photons by matter, meaning that there is an exchange of energy and a change in the light's direction. Typically, this involves vibrational energy being gained by a molecule as incident photon from a visible lesser or shifted to lower energy. This is called normal Stokes Raman scattering, and because it is due to the vibrational change, Raman spectroscopy is very comparable to IR spectroscopy, and that is the reason we are studying here. So, though there are different type of scattering, our today's discussion is on Raman scattering. So, by using a Raman spectrometer, a spectrometer which was specifically designed, or you could say fine tuned by C.V. Raman, the Nobel laureate, so that you can see a very tiny fraction of the scattered light has a different color. It has changed the frequency because during the scattering process its energy changed by interacting with the molecular vibration. This is the Raman scattering process, named after its discoverer, the famous Indian physicist C.V. Raman. By studying the vibration of the atoms, we can discover the chemical composition and other useful information about the material. The Raman effect is very weak, only about 1 part in 10 million of the scattered light has a shifted color. This is too weak to see with the naked eye, so we analyze the light with a highly sensitive spectrometer. So, we are talking about inelastic scattering. So, the ray comes, you see, and then it goes through, and a general major scattering, the elastic scattering, is called Rayleigh scattering, which we talk about, but then there is another one with a little difference in energy. This is called inelastic or Raman scattering. This is the energy transfer from incident light to the molecular vibration. So, Raman spectroscopy is used to determine the molecular motions, especially the vibrational mode of motion. Little bit coming to the history, in 1922 Indian physicist C.V. Raman published his work on the molecular diffraction of light. In 1923 inelastic light scattering is predicted by A.S. Meckel. 1928 Landsberg and Mandelstam see unexpected frequency shifts in scattering from solid crystal. In 1928 C.V. Raman and K.S. Krishnan see feeble fluorescence from neat solvents. This is the first Raman spectra, where they use filtered mercury arc lamp spectrum, and you see the characteristic inelastic ones. So, they published, C.V. Raman and K.S. Krishnan and published this work in Nature with the title A New Type of Secondary Radiation. You all know about C.V. Raman, I will little bit talk about K.S. Krishnan. Kariya Manikkam Srinivasa Krishnan, he is a great physicist and we majorly known him for his contribution to this Raman spectroscopy, but even being a tragic hero who did not get a Nobel Prize, being directly contributed to the invention, he was a postdoctoral worker, he further go to Dhaka University, he joined Santilal Banerjee, B.C. Guha and Ashutosh Mukherjee and developed an elegant and precise experimental technique to measure the magnetic anisotropy of diamagnetic and paramagnetic crystals. So, this is also a very significant contribution, and K.S. Krishnan was a very humble and noble person as identified by many greats at that time, including that time Prime Minister Jawaharlal Nehru. He is the first awardee of the Santi Sarup Bhatnagar award. So, this is little bit about K.S. Krishnan, and this is the Raman spectrometer which we are talking about in Calcutta in the institute IACS. It is kept there as a memoriam, which is the first in endogenous setup of Raman's lab, who have identified the spectra using this spectrograph. Continuing with little bit of history, in 1930 C.V. Raman wins Nobel Prize in Physics for this contribution. In 1961 invention of laser makes Raman experiments reasonable, which we are going to talk about. In 1977 surfaced enhanced Raman scattering or SERS is discovered. In 1997 with the increased sensitivity to the instrument, it goes to such a level where single molecule SERS is also possible to study. So, Raman spectroscopy is a spectroscopy technique used to observe vibrational, rotational and other low frequency modes in a system. It relies on inelastic scattering or Raman scattering of monochromatic light, usually from the laser in the visible, near infrared or near UV range. The laser light interact with molecular vibrations or other excitations in the system, resulting in the energy of the laser photons being shifted up or down. The shift in energy gives information about the vibrational modes in the system and are very characteristic. So, if you see, we are talking about in the infrared level there is elastic or relay scattering, and for Raman it is Stokes and anti-Stokes. So, we have discussed, but vibrational energy levels, these are less energy level than electronic energy level. In between we talked about when we were introducing spectroscopy. The spacing between energy levels are relatively small, 0.01 to 10 kilocalorie per mole. When IR radiation is absorbed, molecules are excited from one vibrational level to another, or it vibrates with higher amplitude. So, this is vibration of a diatomic molecule. It approximates an oscillating spring, as I talked about. So, there are two type of bond vibrations. Again, I talked about them: stretching vibration or oscillation along the line of the bond. They could be symmetric, as you see here, both are having a symmetry, and asymmetric. If you see, there is getting small and getting bigger. So, that is asymmetric. And then bending, vibration or oscillation not along the line of the bond, which are in plane it called scissor and rock, out of the plane it called twist and wag. These animations help you to understand the difference between scissor, rock and twist. Infrared spectroscopy is the spectroscopy that deals with the infrared region of the electromagnetic spectrum. So, as I told, both IR and Raman, they both operate on the vibrational level. So, comparison is extremely important. So, IR spectroscopy is the spectroscopy that deals with the infrared region of the electromagnetic spectrum. It is a result of absorption of light by vibrating molecules. In Raman spectroscopy, it is scattering of light by the vibrating molecules. So, we compare them because both comes as a outcome of the effect of the vibration of the molecules. There are selection rules. Infrared, the intensity of a peak is related to the change in the dipole moment associated in going from the ground state to an excited state. In Raman, intensity of a peak is related to the polarizability of the stretch. Non-polar bonds are usually more easily polarized than polar bonds. So, that is where the key, where we find these two technique as competent to each other. So, here in case of IR, more dipole moment, stronger the band. In Raman, the non-polar bond have more tendency to polarize, and the polarizability is measured. So, that is where you get a very nice relation between the two technique, and that would be done by mutual exclusion principle. So, for molecules with a center of symmetry, no IR active transitions are Raman active and vice versa. What that means? So, symmetric molecule IR active vibrations are not Raman active, and Raman active vibrations are not IR active. So, we are taking the molecule carbon dioxide. So, if you see, when it goes in two direction, it is Raman active. When they are going in one direction, it is Raman inactive. When it is Raman active, it is IR inactive. When it is Raman inactive, it is IR active. So, if we look at spectra of carbon dioxide, as I told, when it goes in the two direction, you get a Raman 1335 centimeter inverse, and when it get in the head to head direction, you get IR 2349 centimeter inverse. When it get like in up down, you get IR 667 centimeter inverse. IR versus Raman spectroscopy. Regarding the excitation wavelength, the Raman technique uses a monochromatic beam or laser in the visible, near infrared or near ultraviolet range of the electromagnetic spectrum. In IR spectroscopy, a monochromatic beam is used in the infrared region of the electromagnetic spectrum. In the IR technique shows irregular absorbance lines depending on the material investigated. The Raman spectrum mainly comprises of elastic scattered light line Rayleigh and two equally distant lines Stokes and anti-Stokes. Advantage of Raman over IR: water can be used as solvent. So, very suitable for biological samples in native state, because here you could use water as a solvent. Although Raman spectra result from molecular vibration at IR frequencies, spectrum is obtained using visible light or NIR radiation. Glass and quartz lenses, cells and optical fibers can be used. Standard detectors can be used. That is the advantages of Raman. Totally symmetric vibrations are observable. Raman intensity is proportional to concentration and laser power. So, easy to calculate. Now, advantage of IR over Raman: simpler and cheaper instrumentation, less instrument dependent than Raman spectra, because IR spectra are based on the measurement of intensity ratio, lower detection limit than normal Raman. We are not talking about resonance Raman, that is coming. So, we are talking about normal Raman. The detection limit of IR is lower. The background fluorescence can overwhelm normal Raman due to its weak signal. More suitable for vibration of bonds with very low polarizability, because with low polarizability you cannot measure them by Raman. So, we have talked about the basic of IR spectroscopy and how it is applied to getting spectra, and how to identify the functional groups, which have number of applications, and they also have some fingerprints which are very convenient to detect presence of a lot of small molecules. Then we have shifted to Raman, compare between IR and Raman, and we also talked about how IR work over the identification of the secondary structure of protein. In the next class, we will discuss about Raman spectroscopy and its application in studying protein, and a very interesting and a novel instrument setup which is called Raman microscopy and Raman crystallography. We will talk about them, and we will also talk about how this Raman crystallography would be utilized towards development of a detection of a live experiment. This is a very smart and novel setup where you could study a real enzymatic reaction, how it is going on, how it is changing the molecule or the compound's chemistry. We will see that in the next class. Thank you very much.